Laminar jamming structures consist of a stack of flexible strips subject to a pressure gradient. In this video, we show that these structures can transform the dynamic response of robotic structures and systems. First, we demonstrate two static capabilities of laminar jamming. When no vacuum is applied, laminar jamming structures behave elastically and are compliant. When vacuum is applied, the structures still behave elastically, but their bending stiffness is far greater. In fact, it increases by a factor of n squared, where n is the number of layers. When vacuum is applied and large deformations are imposed, the structure behaves plastically and dissipates energy, allowing it to take arbitrary forms. Now we demonstrate the dynamic capabilities of laminar jamming structures. First, we modulated the dynamic response of a soft structure. Here we adhered a jamming structure to a substrate composed of silicone rubber. First, we dropped a small metal sphere in the system when vacuum was applied to the jamming structure and when vacuum was not applied. With its low kinetic energy, the metal sphere only caused small deformations, and the jamming structure behaved elastically in both cases. As expected, there was negligible difference in the rebound height of the sphere. Next, we dropped a baseball in the system. When vacuum was not applied, the jamming structure again behaved elastically, and the ball rebounded far away from the testing platform. When vacuum was applied, the high kinetic energy of the ball caused large deformations of the jamming structure. The structure dissipated energy, and the response was heavily damped. We then used laminar jamming to optimize the dynamic response of a UAV on landing. To do so, we built landing gear that consisted of 4 jamming structures. We hypothesized that there was an ideal vacuum pressure for the structures, such that peak forces on the UAV would be minimized without the chassis of the UAV striking the ground. At different vacuum pressures, the UAV demonstrated distinct landing behavior. When no vacuum was applied, the chassis of the UAV immediately struck the ground, and the UAV was rattled. When high vacuum was applied, the jamming structures did not deform enough to dissipate energy, and the UAV bounced. However, at moderate vacuum pressures, the structures did deform enough to dissipate energy, and the landing was far smoother. Please see our paper for detailed models and simulations that can enable designers to tune this dynamic behavior as they wish.